we have an alcohol here, benzyl alcohol, and then we're going to make an amide. You recognize up to this part, it's going to be that part. So this is an alcohol, we have an amide, so we probably have to have a carboxylic acid from that. So one can imagine that, yeah, sure, that carbon need to get oxidized to carboxylic acid in order to make an amide. So just chromic acid or dichromate will oxidize this primary alcohol to the benzoic acid. Then you notice that there's an amine here that you need to add. So carboxylic acid, and if you put it with an amine together, that's not going to work, right? We talked about that. In order to make an amide, you just cannot simply use a carboxylic acid and amine. Even though you may add a proton there, it's not going to work well. So what you need to do, you have to make this carbonyl more activated. One way to do that is making acid chloride. And you can make an anhydride. In order to make an anhydride, you need an acid chloride anyway. So acid chloride is a very easy way to go. You need to treat thionyl chloride, replacing OH with a chlorine. So you get the acid chloride. Now these chlorines are reactive. So amine that you want to use it there is going to make an attack, right? That's going to make a tetrahedral intermediates. But since we have a leaving group, what it do, it will make the carbonyl back and then make the chlorine goes. That basically forms an amide if this proton goes away. So works. So this is actually a much more straightforward answers compared to question that we discussed previously. So you got to recognize what goes, how it goes, what the action does, and what you need to do. Sort of, you've got to make some blueprints and execute it out, making sure there's no errors. Just want to show you the differences between the carboxylic acid derivatives and the ketones and aldehyde here. If you think that you may oxidize this primary alcohol with a PCC, then you will get an aldehyde there, right? If you react the aldehyde with an amine, that will make ene, not amide. If you just throw it out, this and that looks very similar, right? Almost identical, except hydrogen or the chlorine. The reactivity is very different. So that's why, people argue all the time that, yeah, that almost looks 99% same. Why make a different answer, right? I get this part almost right. I should get the 90% of the credit. That doesn't work. Is a being hydrogen there or the chlorine there makes a huge differences for the reactivity, and then you will end up having a different product. That's a ketone and aldehyde. You react with an amine, this will make an attack, but since there's no leaving groups, it's going to get processed to make an amine. But carboxylic acid derivative, you have a leaving group, so that goes. That's the reason why we get a substitution and then make an amide. Very different reactions. So reactions in chapter 18 doesn't really work the same way the reactions in chapter 21. You really need to separate them, even though they may look similar. And then they may use the same reagents. So that's my fair warning. Don't get confused between those two chapters. All right. Let's talk about these reactions. The first one, we have an ester treated with an amine. Ester is not as reactive as acid chloride or the anhydride, but amine still can make an attack to the carbonyl, right? So amine does make an attack. It will make a tetrahedral intermediate. Then what happened was it can kick out the methoxy groups by making the carbonyl. So it will make an amide. So this is a forming amide from the ester. It's something that some of you will recognize. The next one is just a long step. sometimes we want to see whether you can follow each steps properly so you can get to the end. In order to do that, you got to know what this reagent does, right? Lithium hydride, you know that reagent is going to reduce carboxylic acid to primary alcohol. Right? So if you treat that, you're going to make this carboxylic acid to primary alcohol. And the second step, water there, doesn't even need to put on it, but I just put it there, just to make sure that it's going to be warmed up. But even though the water's not stated clearly, you should assume that there's a walk-up steps in every end of the reaction. Meaning that treating the carboxylic acid with the lithium hydride after the end of the reaction before you're adding water is going to be O minus. What water does, it gives a proton to the alcohol. You get a neutral product in the end. So that's what we call walk-up step. So the second step just walk up. Anyway, so you get the alcohol from the carboxylic acid. The second step, I wish you still remember what this PSCl means, right? Tosyl chloride. Primary alcohol will be tosylated, and then tosyl groups will become a very, very good reagent. If there's a nucleophile, you can make an essential reagent. And then, yes, number 4 step, we got the sodium cyanide. Cyanide is a nucleophile. That's the one. Come make an attack, and then kick this tosylate out. So you get the cyanide. So you're just following each step properly to get to the end. And just want to mention that carboxylic acid can be reduced by also the borane. I mean, of course, lithium hydride is staying here. But if you want to achieve the same goal, you can use different reagents. Just want to mention that.